All right. My name is Henrik Flodell. I'm Director of Marketing at Alif Semiconductor. And my talk today is essentially asking myself a question. And I'm going to start the talk by answering the question, just so that we can jump right to the end, because that's usually the exciting part. The question is, can machine learning be fast and low power at the same time? And the answer is yes. You can actually pick two in this equation, which I'm going to show you kind of how we achieve. And some of the things that I'm going to talk about you've heard mentioned in some of the talks that were before me. But just before I get into it, since we are reasonably new, Alif Semiconductor is a semiconductor supplier, general purpose microcontrollers. You can think of us in the same way that you think about other companies where you go and buy your MCUs, MPUs, those kind of things today. The thing that we do a little bit different is that we have really worked very hard from the ground up to try to make our devices very intelligent and very densely packed with functions that we know that the designers of embedded systems will need in their systems. So instead of just providing a core and some peripherals, we want to put as much as that as possible of that into the silicon that our customers get from us, just to help them design their products faster. Essentially how we do this is that we provide processors that enable a very scalable continuum of performance that goes all the way down to single core microcontrollers, highly optimized for ultra low power consumption, and scales up from there to multi-core devices that combine MCU cores and MPU cores on the same die. So you can run real-time tasks in parallel with embedded Linux in the same chip. We have spent a lot of time and effort on engineering our silicon architecture to enable long battery life for applications. Everything that we do is kind of designed on a foundation of ultra low power type processing, and we carry that with us as we move up the performance continuum that I mentioned with the scalability. So there is ultra low power to be had at each of the performance points that our devices cover. We know that microcontrollers tend to be used in connected applications today, and they are also used in a lot of contexts where the data that they process need to be kept secure. So we have also integrated some very strong security from the ground up, again, in our devices. In fact, we integrate a complete secure element implementation in our systems to protect the data on the device, the data in flight if it's participating on a network, and to provide security services for the code that is running on the various MCU and MPU cores. We integrate a lot of functionality besides the processing in our devices as well in terms of peripherals, integrated memories, both RAM as well as non-volatile memory. We've taken the approach that we want to try to include as much of this as possible in the device itself, so that users of Alif technology don't have to go outside our SoC to put their system together. And we have based our silicon architecture on manufacturing technology that allows us to create very small packages, even though we do integrate all of this functionality. And the final thing that we did when we sat down and kind of looked at what we wanted to achieve was to try to look, 2 years, 3 years, 5 years from now, how are the developers going to want to solve their problems? And when we went and talked to customers, they told us that we find machine learning fascinating as a topic for a number of different reasons. The two main ones was either I'm solving problems in a certain way today, and I believe if I had access to efficient machine learning in a microcontroller, I could improve the efficiency of the way that I do this in my current product. And the other one was, I had this idea for a product that doesn't yet exist, but I can't find a device that allows me to do the machine learning that I would have to employ in order to solve the problem. So that was something that we really wanted to integrate as well. And we realized that if we are able to integrate this, if we're able to cover also the machine learning aspect, we actually improve the scalability, because we can offload the machine learning processing to accelerators that can handle that. So we get even better scalability. We can improve the battery life, because as soon as the machine learning processing is done, we can go back to sleep, and the device won't be consuming power anymore. And also, in terms of the security, if we can keep the data on the device, we improve the privacy for the system in general. So we've created a lineup, and I'm not going to go through the full specs of what we're doing. We're at the expo. You can come visit us, so we can talk about it. But we have a lineup of devices, like I said, at scale from single-core MCUs to dual-core MCUs. And we have something that we call a fusion processor, where we combine MCU cores and MPU cores, triple-core devices and quad-core devices, where you have two MPU cores operating symmetrically, and then two real-time cores in the system as well for those kind of tasks. We use ARM-based technology. We've tried to, as much as possible, keep the IP that we're using on the application side of our devices, let's call it standardized, right? So that people, when they pick up an Alif device, they know what they get. It fits into their standard workflow. They can use their standard tools to work with it. And it also helps improve the scalability because this is kind of well-known quantities. People are very familiar with ARM-based architecture today. We did the same on the machine learning side. We've taken the Ethos-U55 micro MPU acceleration units from ARM. We actually have multiple Ethos-U55s in our system, depending on where on the performance continuum you land. And they scale all the way up to 256 max per second in terms of operation. And then on the MPU side, we employ these A32 cores that can go all the way up to 800 megahertz. So it's an amazing amount of power, just compute power, in a very, very small package. The size of the largest device in this series, the E7, is about 6 by 7 millimeters, and it goes down from there. What we're doing, so to kind of get back to the topic at hand, to combine machine learning and low power consumption, we set up an architecture for our system where we have essentially divided the device into domains and operating regions. And these smart domains that we've created are separated depending on which functions that each domain perform. The domains can be independently controlled, switched on and off, and we also have some IP in the device that we have designed that can help developers essentially power down a domain when it's not being used by any code that is running in the system. So it kind of autonomously handles that. And then in terms of the regions, you see here in the graph, there's kind of three main bands of regions. There's an always-on region. You will always find that in a microcontroller. Whenever you put it in the very lowest power mode, some things need to be active so you can wake it back up again. What we did that is a little bit unique is instead of having that A-on region and then go to the next step, which is now everything comes back on, we implemented a dedicated high-efficiency region in our devices, which is a separate compute environment with a separate machine learning accelerator, a separate microcontroller core that can be kept awake, but is instantiated using the most efficient silicon processes that we can employ. So you essentially have, we call it the sniffing engine, something that can sense the environment around the device and operate with machine learning capabilities, if so chosen, but maybe a lower fidelity model, something that is not as compute intensive as if you were to, say, be able to detect a specific person. It can detect that it's a humanoid shape that is approaching. So you can have this high efficiency region operate, and it can sense the environment around the device. And when it detects something that crosses a threshold and triggers a need to do a more in-depth analysis of what is going on, it can wake up a high performance region that contains essentially the rest of the system that will be able to go in, do that in-depth classification, and come up with a very detailed result, and then take an action if that is warranted, depending on what the situation is. We started collaborating with Edge Impulse about a year ago now. It was just around the time of the last Imagine conference. And once we had worked with them long enough to get full support for our devices into the Edge Impulse environment, we started running some benchmarks because we've seen some really impressive data kind of on models that we've designed, that some of our software partners have designed on our silicon. And we just wanted to compare with some of the tutorials in the Edge Impulse system with what you see when you run that on the Ensemble silicon. So for these two graphs here, we're using the responding to your voice tutorial that is in the Edge Impulse framework, and we've kind of indexed the results to what we saw when we ran this tutorial on the high-performance MCU core with its Ethos accelerator. We indexed that to 1, and then all the other numbers you see is how many times more it took to run it on those platforms. So high-efficiency core 2.8, so it's slower, but comparatively not by much. The thing that is kind of standing out to me is the fact that we're 115 times faster than a Raspberry Pi 4, and that's a beast of a device, right, compared to an MCU. Same thing with adding sites to sensors. So this is kind of the vision use cases, and it was always difficult for microcontrollers to go down to vision. Voice, kind of okay, depending on what it is that you're doing. Vibration, yeah, they can handle that. But vision becomes difficult in MCUs. When we run this tutorial on our high-performance core, we can go up to above 700 frames per second of throughput. The high-efficiency core is slower, but again, the Raspberry Pi 4, significantly slower than both. So we really have been able to architect a system that can take machine learning and execute that at a tremendous pace, and then we have the microcontroller cores to do all the other tasks of the application available. So essentially answering the question, yes, it is very fast, and with that speed comes power efficiency, because this is kind of a comparison of a demo. We actually have this demo in the expo. This is MobileNet V2 running on our Ensemble device, CPU bound and accelerated. So you see the inference time when we're running it on the CPU core alone, it's about 2 frames per second when we're doing image inferencing. Doing audio inferencing, it's faster, but it's still a lot slower than when we turn the M55 on. So we dropped the inference time from 624 milliseconds down to 8. And because we can finish it that much faster when we have the U55 on, even though in that moment the power consumption is higher because you have 2 things running in at the same time, the energy that is consumed by the operation drops by a factor of 75, right? You go from 228 to 3 millijoules in the system, and that means in the long run you save a tremendous amount of power. We've done a whole bunch of these kind of math exercises and use cases for various applications. This is for a peel and stick type camera for kind of a home alarm system that has a duty cycle where it needs to sense what's going on around the camera for some interval. And then every once in a while, something will happen that will require our system to wake up the high-performance core to do more advanced processing. And for this duty cycle here, and I mean, all the duty cycles are different, right? But in this one, you see that we can take the power consumption over a 24-hour period down from 240 milliamps down to 9. So 27x longer battery life. That's pretty good for a very integrated microcontroller system. We have demos in the expo to show you this. We have more information about the lineup of our microcontrollers, what they can do. I'd love to talk to you about what you would like to do with a device like this. There's also more information on our website, alifsemi.com. Come visit us. Thank you.